I've done over 25 senior Python developer interviews for roles up to $200,000 in total compensation. And I've compiled this list of 50 advanced Python concepts that you need to learn to secure senior level Python developer positions. This job market is tough on everyone right now, so now is the time to set yourself apart from all the other drones that are just spamming easy apply. These 50 concepts will give you an advanced understanding of the Python programming language and allow you to really shine in most senior developer interviews. You don't need a 10-minute video to understand each concept. In this video, I'm going to show you just what you need to know, along with a visualization so that you can learn these as fast as possible. These concepts are focused around building performant applications and memory management, which are key concepts that any senior Python developer should master. So let's get into it. Arrays. What are Python arrays? I got this as the first question for a £150,000 interview for a UK company, and it threw me off completely. You might think Python arrays are just another name for lists, but that's wrong. Python's standard library includes the array module, which provides a type-specific array structure. Use this when you need a simple type-specific array and want to save on memory. When creating an array, you need to specify the type code, which defines the type of elements the array will store. Some advantages of arrays are they're more memory efficient than lists because they store elements of the same type. They can enforce types as well, which can prevent accidental type errors. And operations on arrays are faster than lists when working with large datasets of the same type. But of course, an array can only hold one type, and you miss on a lot of the flexibility and functionality of lists, such as dynamic resizing without type constraints. Python garbage collection. Python manages memory automatically, but there's one scenario where it can really struggle: circular references. In this example, we create two node objects that reference each other. Even after deleting A and B, the memory they occupied may not be released because Python's garbage collector can't resolve these cycles easily. We can then force garbage collection to clean this up. So as you can see, even after deleting both A and B, we force garbage collection and we still collected two objects. Dictionaries and lists you don't need to return in other functions. Let's say you have one function that takes in a list, returns that list, and then you have another file where you import that function, initialize a list, pipe that list into the function, reassign it, and then print it. This works. You don't have to return the list and reassign it. For example, you can go into the function, remove the return statement, remove the reassignment, and you'll still have the same results. This is because objects like dictionaries and lists retain a strict reference in Python. So no matter where you send your list or your dictionary, it will still perform operations on the original object. So you don't need to return anything. I just want to say that all code examples shown in this video are going to be publicly available on the GitHub repository. Check the link in the description for that. And if you find anything that could be improved, feel free to submit a pull request and contribute to the project. Python method resolution order. This is something you might already know, but if someone asks you in an interview, you might struggle to explain it. This determines the sequence in which classes are searched for a method or attribute. This is especially important in cases of multiple inheritance, where a class is derived from multiple parent classes. The MRO ensures that Python knows the exact order in which to look for attributes and methods. What you should know is Python uses the C3 linearization algorithm to determine the MRO. Basically, it will go from left to right. Now there's something called the diamond problem, which occurs when a class inherits from two classes that share a common ancestor. This can lead to unexpected behavior if not handled properly. The Walrus operator, officially known as the assignment expression. It's represented by a colon and then the equal sign. The Walrus operator allows you to assign a value to a variable as part of an expression. This can make your code cleaner and more concise. Let's look at an example. Let's say you have a function that takes in a dictionary that can contain very different keys. Suppose you want to look for a specific key, and if that key exists in a dictionary, you want to return that value. With the Walrus operator, we combine this lookup and this check in one line of code. So we first assign my variable, and check if it's truthy, and if so, we return it. This may seem very trivial, but it's just one of those tiny details that can show the interviewer you really know Python well. Operator.attrgetter. Suppose you have classes nested in another class. Here, person has address and company, which are both classes. You initialize a list with a bunch of persons. Each person has the address and the company. And let's say you want to sort either by the city name of the address of the person or the name of the company of the person. It can take two values. The cool thing about attribute getter is it can take a dynamically generated string and use it to look up nested attributes. This means that if you want to go even deeper in the nesting, you can build on the sort key by appending more attributes to it. This is very useful if you're building automation systems where the user can set up what attributes will trigger what reactions, etc. Because then you can go really deep on the nesting and give them some really good flexibility in their applications. You could also implement something similar with a lambda expression, but this is faster than lambda because attribute getter is implemented in C. CPython. CPython is the default and most widely used implementation of the Python programming language. When people say Python, they're often referring to CPython. It's written in C, no surprise there, and serves as both an interpreter and a runtime for executing Python code. Some cool things to know here is that Python code is first compiled into bytecode, which is then interpreted by the CPython virtual machine. It also comes with Python's extensive standard library, making it versatile and powerful for various applications. Another feature which we'll cover in another concept is the global interpreter lock. This is a mutex in CPython that ensures only one thread executes Python bytecode at a time, simplifying memory management but limiting multi-threading performance. Some strengths are it's very beginner friendly, has a straightforward installation and setup process. It's also widely adopted. It of course supports writing C extensions for Python, and this enables performance critical parts of a program to run in C, which is very useful. And this has some drawbacks, mainly the GIL has some drawbacks, which we'll go through later. It's slower compared to compiled languages like C or Java because it interprets bytecode at runtime. The global interpreter lock is a mechanism used in CPython to ensure that only one thread executes Python bytecode at a time, even on multi-core systems. While the GIL simplifies memory management in CPython, it imposes significant limitations on multithreading, particularly for CPU-bound tasks. So why do we have this? Well, CPython uses a technique called reference counting to manage memory. Objects are automatically deallocated when the reference count drops to 0. The GIL ensures that reference count updates are thread safe without requiring additional locking mechanisms. With this, we can also avoid race conditions, since if we have multiple threads updating shared objects, this could corrupt the interpreter state, which leads to undefined behavior. So how does the GIL work? It allows only one thread to execute Python bytecode at a time, even on a multi-core CPU. So threads take turns holding the GIL. A thread must acquire the GIL before executing, and the GIL is released after. And the GIL is released either when the thread encounters I/O operations, such as file or network access, or periodically during long-running operations to let other threads run. Now, because of this, multi-threading in Python does not achieve true parallelism because the GIL restricts Python threads to execute one at a time. This makes multi-threading ineffective for tasks like numerical computations or image processing. Important to note here is that the GIL does not affect multiprocessing, which is a concept we'll go through, because each process has its own Python interpreter and GIL. So in multi-threading applications like this one, despite having 4 threads, the execution time will be similar to a single-threaded program due to the global interpreter lock. Concurrency. Concurrency in Python allows a program to perform multiple tasks at the same time or handle multiple operations simultaneously. It doesn't necessarily mean tasks run in parallel. which would be simultaneously on different processors. Instead, it refers to managing multiple tasks efficiently. Python offers several concurrency mechanisms, such as multithreading, multiprocessing, and asynchronous programming. We mentioned parallelism a bit. What are the differences between concurrency and parallelism? Concurrency manages multiple tasks simultaneously, but not necessarily executing them at the same time. They're sort of interleaved by something called context switching. Parallelism executes multiple tasks simultaneously on different processors or cores. Now, some challenges in concurrency are thread safety. Since threads share memory, this can lead to race conditions. So concurrency can also introduce non-deterministic behavior, which can make bugs harder to reproduce and debug. And of course, there are limitations by the global interpreter lock on achieving true parallelism. Multithreading. Multithreading in Python is a way to achieve concurrency by using threads, lightweight subprocesses that run within the same process. Threads share the same memory space, making them efficient for I/O-bound tasks where waiting is common, like reading and writing files or network requests. Multithreading is essentially a lightweight way of achieving concurrency, since threads use less memory than creating multiple processes. Now, a thread is the smallest unit of a process that can execute instructions. But because of the Python GIL, only one thread can execute Python bytecode at any given time. But when we do I/O-bound tasks like network requests, where we can be waiting for a response, this is still beneficial, as then we can switch to another thread and execute other code. Let's say we have 3 URLs to download. We initialize 3 threads here and have them all download a different URL. As you can see, all 3 start at the same time. This way we can toggle between each download while waiting for the results. Managing many threads manually can be a bit complex. So for this, we're going to use the thread pool executor to help out. This makes thread pooling a lot easier. This automatically manages our thread life cycles and gives us cleaner code for running tasks concurrently. If you found value in this video so far, please consider giving me a like and subscribing to this channel. And leave a comment if you want more advanced Python programming tips. I make videos to help self-taught programmers break into AI engineering, get better at Python, and earn more. So if you're interested in that, feel free to check out my other videos. Multiprocessing. Multiprocessing in Python allows you to execute tasks in parallel by creating separate processes. Each process runs independently with its own memory space, enabling true parallelism, unlike multithreading, which is constrained by the global interpreter lock. So some benefits include, of course, true parallelism. It's better for CPU-bound tasks because we can leverage multiple CPU cores. Processes also don't share memory, which reduces risk of data corruption compared to threads. In multiprocessing, a process is an independent unit of execution with its own memory space. We also have a pool of worker processes that execute tasks concurrently, simplifying task management. It's kind of hard to visualize, but here both processes are indeed running at the same time. Disadvantages include higher overhead, as creating and managing processes consumes more resources than threads. Data sharing between processes require additional mechanisms like queues or shared memory, which is a bit more complex. And spawning processes can take time, making it less suitable for short-lived tasks. Managing threading race conditions. Here we have a function with a global variable, and every time it's called, 100,000 times we're going to add a 1 to it. If we initialize 2 processes, have both of them start, and then print the final value, the final value will never be the same. Now we can fix this by using locks. So here we initialize a lock, and a lock is essentially a flag that can be either locked or unlocked. When a process tries to acquire a locked lock, it gets put to sleep. When the lock is released, one waiting process is woken up to acquire it. Locks guarantee that only one process can hold a lock at a single time. There are also other methods of avoiding race conditions you can look into. Locks are just one of many ways you can avoid race conditions in multithreading. Addressing shared memory in multiprocessing. For tasks that require shared data between processes, you can use shared memory via multiprocessing.value or multiprocessing.array. Here we create a shared value of integer I and is initialized as 0. This variable is piped into each process with a synchronization lock. This value is piped into each process with a synchronization lock, and this ensures that only one process modifies the value at a time. Collections module. This module in Python provides specialized container data types that extend the functionality of Python's built-in types like lists, dictionaries, and tuples. These data structures are optimized for specific use cases, making your code more efficient and expressive. This offers additional features not present in the built-in types, and since these are designed for specific tasks, they are faster and more memory efficient in those cases. This also provides intuitive abstractions for common programming patterns, enhancing our code readability. Among these are the default dicts. So for example, we can initialize a default dictionary where each value is an integer. And that means when we assign a new key to it, it will automatically be a 0, and we can just increment it accordingly. This is useful in solving LeetCode problems, for example, where you often have to use a hash map with default values. Similarly, we can import a ordered dictionary. The ordered dictionary is like a regular dictionary, but it remembers the order in which keys are inserted. I encourage you to look more into the other contents of collections, as these tools are often faster and more memory efficient than re-implementing similar functionality yourself. And the specialized data structures make your intentions clearer, which improves code readability. This is huge for solving LeetCode problems again. And it's often used in professional Python projects for clean and efficient solutions. Encapsulation. Object-oriented programming in Python organizes code into objects, which are instances of classes. The 4 pillars of OOP in Python, encapsulation, abstraction, inheritance, and polymorphism, help create scalable, reusable, and maintainable software. Here's how encapsulation applies to Python. Encapsulation is the concept of hiding the internal state of an object and exposing only what is necessary through a controlled interface. It helps protect an object's integrity by restricting direct access to its data. Now in Python, we achieve this by using the double underscore to denote a private attribute. So here we initialize a bank account with a self.__balance. This means that if we try to access the account.__balance, we get an attribute error because we are trying to reference it outside of the context that it's in. Instead, we have to use a getBalance method that retrieves the __balance from within the bank account itself, and then we can call that method. This is how we can ensure controlled access to private variables. As you can see, now I removed the underscores and I can access it outside of the context. So what Python does behind the scenes is something called name mangling, which changes how it references this attribute. Abstraction. Abstraction means hiding the complexity of a system and exposing only the necessary parts. It allows users to interact with the system without understanding its internal workings. In Python, you can achieve this with abstract-based classes and interfaces defined in the ABC module. Classes inheriting from an ABC must implement abstract methods, enforcing a contract for behavior. In this example, the shape class is abstract and cannot be instantiated directly, but when we subclass it with the rectangle, we need to implement the area and the perimeter methods. If we comment these out, we can't even instantiate the rectangle class because it's missing these required methods. Now, of course, to abstract in Python, you don't need to use an ABC. It's just more like a nice little helper to create your skeleton. You can also subclass a regular class, but then it won't automatically enforce the required methods. Inheritance. Inheritance allows a class, or the child, to inherit attributes and methods from another class, the parent. It enables code reuse and establishes a relationship between classes. Basically here we are inheriting a class that is not an abstract base class. This class can be instantiated and should do so in the code. If you never instantiate your parent class, then you should probably use an abstract base class. Now we can still enforce the implementation of certain functions by using the not implemented error. And this is something you'll see common in frameworks like Django. But again, you should use an ABC if you're not instantiating the parent class. It makes the code just so much more readable, and then you can utilize these nice features of ABCs. Another reason to use an ABC is when you want to define a common interface for multiple related classes, and you really want to enforce this contract that child classes must implement. Polymorphism. Polymorphism means many forms. The same interface or method can behave differently depending on the object. In Python, we achieve this with method overriding in subclasses. Functions or methods can operate on objects of different types if they share a common interface. Here we have a rectangle and circle, and they're both subclassing the shape class. So basically these 4 pillars are like design patterns for making reusable code. When you use subclassing in Python, you're already employing several of these pillars, so they kind of work together in that way. By understanding and applying these pillars, you can design Python programs that are easier to maintain, test, and extend. The Python data model. The Python data model, oftentimes called the Dunder or magic methods model, defines the standard way for Python objects to interact with the Python interpreter and with each other. This provides a framework of special methods, which are surrounded by double underscores like init and len, which allows objects to implement behavior like arithmetic operations, iteration, attribute access, and more. So by learning the data model, you can make your custom objects behave like built-in Python objects, leading to more intuitive and powerful APIs. This will also enhance your code readability, and having readable code is very important to market yourself as a senior Python developer. You most likely encounter the basics such as init, runs when you initialize the new instance of an object, and the repr and string implementations, which are also commonly used in Django. Here, enter is called when you use a with object, such as when you're opening a file. Exit is when you exit the context window. An iterator is an object that implements the iterator protocol. This means that it has a iter dunder method that returns the object itself, and it has a next dunder method that returns the next item in the sequence and raises stop iteration when the sequence is exhausted. Generators. Both generators and iterators are used to iterate over data in Python, but they're not the same. A generator is a specific way to create an iterator, while an iterator is a more general concept. Generators are defined using a function that contains one or more yield statements. Each yield pauses the function and saves its state, resuming where it left off when the next value is requested. Generators are a type of iterable in Python that allows you to produce values one at a time using the yield keyword. They are more memory efficient than lists because they generate items lazily, on demand, rather than storing all items in memory. Note that when we call the generator function, we don't execute it. We have to call next with the generator as a parameter. And each call resumes the function from where it last yielded. We can also send a value into the generator and resume its execution with the gen.send command. Now the yield expression receives the sent value. So to summarize, an iterator can be anything from a tuple to a list to a generator. A generator is a type of iterable that generates items lazily rather than storing them all in memory. If you have an interview question asking you to optimize for memory, you can often bring up the concept of generators to accomplish this. Static methods and class methods. These differ from regular methods and classes because they do not receive the instance object. Class methods receive the class as a parameter. This means that you can call it from the instance level and the class level. For example, is valid transaction for this bank account? I am calling directly from the bank account class. As you can see, I can also call it from the instance. This is great when you passed the instance to another file in your code, which means you can call the class function without importing the class itself. You just call it on the instance itself. Now, a static method is the same as a class method, but it does not receive the class as a parameter. So this you should use if you're not tampering with the class at all. You should always make a static method because it makes your code just so much more readable. Class methods you use on operations involving the class itself, or factory methods, or alternative constructors. Dependency injection. Dependency injection is a design pattern where dependencies, that's objects or values a class or function requires, are provided externally rather than being created inside the class or function itself. It promotes loose coupling and makes the code more testable, reusable, and maintainable. Here I have a payment processor class that creates its own payment service, that is the PayPal service. This tightly couples the two together. This can make testing a lot harder. You can't easily override this and provide another payment service like Stripe. With dependency injection, we create the dependency outside of the context and then inject it as a variable here. That way it will be way easier to test this because we can send different payment services to the same class. This particular injection is called a constructor injection because we are passing the PayPal service directly to the constructor here. Dependency injection offers flexibility as dependencies can be easily swapped or replaced without modifying the consumer. It's very testable, and it helps you write more maintainable code because changes to dependencies won't require changes to the consumer. Now, dependency injection can increase some complexity, and it can be a bit superfluous and add too much overhead in small applications. Did you know that with PyTest, you can pass in an array of different variables you want to send into the function? So here I have test get user details and expects a user ID and an expected name. All I need to do is just add these to the list here, and I can add more as I go. This makes your test so much readable and faster to write. These fixtures are a powerful way to set up and clean up your test environment. By using the PyTest.fixture decorator, this function will call once you start running the tests. Whatever you yield will be injected into the test. And after the yield statement, you can do cleanup. Once the test is done, this code will execute. This is very useful when you're testing operations to your database, so you can set up the connection once the tests are run and close it once you're done testing. It also allows you to maintain the same database connection across multiple tests. This you definitely need to know as a backend developer, because if you're testing database operations with your API, you want to set up the database once, run your tests, and then close the connection. Serialization and deserialization. So serialization is useful for storing data because we can save certain objects to disk like configurations or machine learning models. We can also send the data over a network in a format other programs can understand. We can cache the data, and we can share the data between multiple systems using a common format like JSON. A way to serialize in Python is with the pickle library. So we have this person class, we create an instance, and we're able to save this instance of the file to a pickle object and then load it to a pickle file. And then we can deserialize this pickle file and continue using the person in the same state that it was saved. Getstate and setstate. We can customize pickling with the getstate and setstate dunder methods. These are built into Python but mainly used when pickling objects. So if a class contains attributes that cannot be pickled, like file handles, threads, and sockets, we need to customize the serialization. For example, here we're assigning self.file to an open context of this file name, which cannot be serialized. So in the getstate method, which is called when we're pickling the Python object, we simply remove this unserializable attribute. If we don't do that, we can get a type error. Similarly, the setstate is called when we are loading the pickle file. And here we can restore the file object. heapq. The heapq module in Python provides an implementation of the heapq algorithm. also known as the priority queue algorithm. A heap is a binary tree-based data structure where the parent node is always smaller in a min-heap or larger in a max-heap than its child nodes. Now, heapq implements a min-heap by default, and it's efficient for finding the smallest or largest elements in a collection. So common operations like heap push and heap pop have an O log n time complexity. Whenever you deal with a problem that could be solved with a heap, you should use the heapq library, as the implementation is already done for you. Unless, of course, you're doing lead code, in which case you would probably need to implement the heap yourself. You may be looking at this and wonder, why don't we just use a list? Whenever you're inserting to a list, the worst case scenario is an O of n time complexity, because you need to shift all the existing elements one step to the right. Also, removing the highest priority or the lowest value item is O log of n time complexity compared to O of n with the list. Now, they really shine when you need to find the highest priority, or let's say the lowest value. This is an instant lookup, or O of 1 time complexity versus O of n in an unsorted list. So here we have a simple task scheduler, and when we add a task here, because we're using the heapq heap push method, we can assign the priority of this task and it will add it to the heap in O log of n time compared to O of n time for a list. Then we can execute the highest priority task in O of 1 time because it is the first node in this heap. Higher order functions. A higher order function is a function that either takes other functions as arguments or returns a function as its result. This concept is a cornerstone of functional programming, allowing for flexible and reusable code. Python supports higher order functions, and you encounter them often in common programming tasks. For example, here we have the validate function, which can take in additional functions, and this can customize how we validate the input data, which can make our code very dynamic. This is also something you'll see a lot in frameworks like Django, where you can add a list of validators to your field. This is good because you can reduce the boilerplate of your code by abstracting patterns. It allows for a lot of flexibility, and you can encapsulate reusable logic and functions that can be applied in multiple scenarios. Filter. This is a higher order function that you should know about. You can use filter to filter elements in an iterable based on a predicate function, which returns true or false. In this simple scenario, we use this lambda function to determine if it's an even number or not, and it will only return the elements that pass this requirement. I know this may seem trivial, but a lot of you would just create a for loop with if statements, which is more lines of code, and let's face it, one-liners in Python are sexy, and you're using standard library classes, which demonstrate your deep knowledge of the Python ecosystem. Advanced list comprehension. You should know that you can use nested loops in list comprehensions. For example, here we have a 2D matrix, and we can loop over first each row in the matrix, and for each row, we loop over each number in this very sexy Python one-liner. You can also use conditional expressions to return different things depending on a true or falsy outcome. And you can even call functions in your list comprehension. These techniques will extend the usability of your list comprehensions, which makes your code more readable and faster. This is not a Python specific concept, but understanding this is important to Python programming. Bytes is a fundamental data type in Python used to represent binary data. It is immutable, meaning its contents cannot be changed after creation. A bytes object is essentially a sequence of integers in the range of 0 to 255, 8 bits per value. This is often used for low-level data manipulation, communication, or file I/O. Now, many real-world applications involve working with binary data, such as images, audio files, or network packets. Also, when working with hardware, network protocols, or file formats, binary data is often required. It's also more efficient and compact to store binary data compared to strings or other formats for raw information. In Python, if we want to transform a string into bytes, we simply add the B character before the string. And this is how we can write a string to a binary file. And then when we read the file, we can print the data which will end up in bytes. Python bytecode and the dis module. Python is interpreted, but its execution model involves an intermediate step, bytecode. When you run a Python program, the Python interpreter compiles the source code into bytecode, which is a lower level platform independent representation of your code. This bytecode is then executed by the Python virtual machine. So the dis module in Python allows you to disassemble Python bytecode to inspect and understand how your code is executed at a lower level. And inspecting bytecode can help you understand how Python translates high-level constructs and identify redundant or inefficient operations, which will ultimately help you optimize your code. It can also help with debugging complex logic or simply help you learn more about Python's internals. Memoryview. Imagine you're parsing a large binary file, such as an image or a network packet. Instead of reading and copying parts of the data repeatedly, you can use memoryview to work directly on slices of the file. For example, here we have a very large data set. Now, if we slice it regularly, we actually create a copy of this. But if we slice using memoryview, we're just viewing the data. There's no copy being made. And we can visualize this by printing out the memory usage of each slice. As you can see, the difference is huge. So using memoryview is an excellent way to optimize memory and create more performant applications. Metaclasses. When you create a class in Python, Python secretly creates an instance of the type class, which is the default meta class. If the class inherits from something, you would pass this in the tuple as an argument, and this dictionary contains the class's methods and attributes. This is how a class is constructed behind the scenes. This is valuable to know because we can create custom metaclasses, and these inherit from type and override certain methods like the dunder new or dunder init. You see this in frameworks like Django, where when you create a model, it creates a table in the database for that model. Model in Django is not a regular class. It has a custom meta class called model base, which we specify with a meta class argument. When Python processes the myModel class, model base kicks in and collects the fields name and age, automatically generates additional methods and attributes like, for example, the default Django objects, which you use to query the database, and it creates metadata for database mapping. Here's a simplified version of this meta class. So this is what happens when we create the new class. We collect all the fields, we add the meta attribute to store metadata about the model, and we add the custom manager. Now this is all Django specific stuff, but meta classes lets you control how classes behave. So you can use them to automatically add methods or attributes to a class. You can check if a class follows certain rules when it's created, and much, much more. Nesting and combining context managers. When working with multiple resources like files or database connections, you can nest context managers using with. So here we are nesting two open files by separating them with a comma. And now we can access both of the files in the same context. We can also combine multiple context managers with exit stack from the context lib library. When the number of context managers is dynamic or unknown beforehand, you can use context-lib.exit stack to allow you to manage them programmatically. So here we can pass in a list of files that can be of varying sizes, and using stack.enterContext, we can nest these context managers dynamically. The context manager decorator allows you to create context managers using generator functions instead of defining a class with the enter and exit dunder methods. Basically here we can very quickly turn this function into a context manager, which means we can use the with command with here. So when we open the context, this code is executed, and in the finally, this code is executed when we close the context. This is again nice when working with databases, and it's just a quicker and nicer, more elegant way of creating context managers. weakref. To help the Python garbage collector collect circular references, we can use a weakref. A weakref does not add to the reference count of an object, which means that this reference alone is not enough to keep the object alive, and if every other reference is deleted, then the garbage collection is free to destroy the object. Of course, the drawbacks of weakref is it can be garbage collected, so you need to make sure that you have at least one reference if you don't want it to be garbage collected. It also doesn't work with immutable types like tuples. The delete keyword. With this, you can delete objects when you know they're not needed to reduce the reference count without relying on the garbage collector. WeakKeyDictionary and weakValueDictionary. The WeakKeyDictionary and weakValueDictionary classes in Python, provided by the weakref module, are specialized dictionaries that use weak references for their keys or values respectively. These are useful when you want objects to be garbage collected even if they are referenced in a dictionary. Here we have a widget class and we create widget metadata using a WeakKeyDictionary. Here we instantiate two widgets and we attach two sets of metadata using the WeakKeyDictionary. Now if we delete widget 1, because widget metadata widget 1 doesn't have any more strong references, it's automatically cleaned up. And we're left with only widget button 2 in the WeakKeyDictionary. This is great because in certain cases, an object should not be kept alive solely because the metadata is stored in a dictionary. Usually when we're working with metadata, whenever the instance that the metadata references is cleaned up, we also want to get rid of the metadata itself. There's also the weakValueDictionary, which has the same feature, except now the referenced object is a value instead. Using slots to reduce memory usage in classes. The slots mechanism is a way to explicitly declare the attributes of a class, preventing the creation of a dynamic dict dunder method to store attributes dynamically depending on what it accepts. This adds additional overhead, and this is how we can reduce the memory footprint of each instance. Memory Profiler. The Python Memory Profiler is a tool used to monitor and analyze the memory consumption of a Python program. It is especially useful for identifying memory-intensive parts of your code and optimizing their usage. It provides insights into how much memory specific functions or lines of code consume, making it a valuable resource for diagnosing memory leaks and improving efficiency. You will need to pip install Memory Profiler as it is an external package, but then you can import the profile decorator, decorate your function, and then when you run it, it will print out the memory usage of that function. This is great for identifying memory leaks in your application so that you can optimize memory usage. sys.getsizeof. This function is used to determine the memory size of an object in bytes. It's a helpful tool for analyzing the memory consumption of different objects in Python, including custom classes. Now this gives the shallow size of the object. This is the memory occupied by the object itself, not including the objects it references. And it's useful for identifying how much memory a particular class or its instances consume. Here we have a basic class and we're going to instantiate it a bunch of times. And we can print the size it occupies in bytes. Advanced decorators. A decorator is a function that takes another function or class as input, modifies or extends its behavior, and returns the modified object. You probably know about decorators already, but there's just so much more to them than logging or timing a function. We can use decorators to attach state, like a counter, to a function. Here we have a wrapper function and a decorator call counter. We set the calls attribute to 0, and then every time we call, we increment by 1. Now, when we wrap our greet function in the call counter, we can print out the number of calls we've done. Similarly, we can use decorators for caching results. Here we check if the args are not in the stored results, well then we update the cache with them. Here, if we have an expensive calculation, we can cache it by storing the results in a dictionary. If we don't find the result in the stored results, we'll do the expensive function. If not, will return it straight from the dictionary. You can also stack decorators, allowing multiple layers of functionality to be applied to a single function. First, the authenticate decorator is executed because it's defined first, and then the log one. You can also decorate classes, and this is useful to resolve the diamond problem compared to when using mixins, because here, when we decorate the class, we can assign the new method. Also, a decorator can take arguments itself, which allows for even greater flexibility. Here, our decorator takes a unit of time, and when we decorate the function, we can specify the type to send to the decorator function. Data classes. The data classes module in Python provides a decorator and functions for creating classes that are primarily used to store data. By using data classes, you can avoid writing boilerplate code like init, repr, and equals methods, while keeping your classes clean and expressive. To illustrate this, here is the manual implementation of the following code. In the constructor, we assign self.x to x and y to y. In the repr, we define a string representation, and we implement the equals method. We also implement the hash method for using objects in dictionaries. We create the init with the type parameters. We generate the repr for nice string representation. We have the equals for equality comparison, hash for using objects in sets and dicts. So this is how we would hash this object. As you can see, if you find yourself doing this a lot, then data classes are for you. You can also define a data class with default values. Now, if you initialize the data class of frozen equals to true, you make the data class immutable. And this prevents modifications to its attributes after creation. So when should you use data classes? If you have classes that primarily act as data containers, when you want cleaner code and avoid using init, repr, and equals, or when type annotations matter for you, because these can help enforce type hints, making code more readable and maintainable. They are also slightly slower than manually written classes or name tuple for large-scale operations. So if performance is critical, look into things like name tuple or structs. Metaprogramming. Metaprogramming refers to the concept of writing programs that can manipulate or generate other programs. In Python, metaprogramming allows you to modify or generate code dynamically at runtime. This is achieved using techniques like decorators, metaclasses, dynamically modifying attributes, and more. Metaprogramming in Python allows you to write code that can manipulate code itself, creating new code, modifying existing code, or analyzing code structures. The functools module. This provides higher order functions and tools that make it easier to work with functions. These utilities are particularly useful for improving code readability, reducing repetition, and enabling functional programming paradigms. So normally when you decorate a function, you are essentially overriding that function. This means you lose access to the original function's metadata like the dunder name or dunder doc methods. If you use the functools.wraps, you actually preserve these two. Using functools.lru cache, you can cache the results of a function so that if it's called with the same arguments, the result is returned from the cache instead of recomputing. So here we have an expensive computation. We wrap this expensive computation with our LRU cache and the max size of 3 results. And as you can see, we only computed 2 once and then cached it, and then printed the result once per function call. Functools.reduce applies a function cumulatively to a sequence, reducing it to a single value. Basically here we're multiplying 1 by 2, and then the product of this we're multiplying by 3, and then the total product of this we're multiplying by 4. That's what reducing does. This is important to know because there are simple implementations for common patterns like caching, function composition, or argument fixing. It can also improve your code readability by replacing verbose patterns with clean and functional abstractions. It will also show in interviews that you understand the Python standard library well and can use those methods instead of trying to implement things yourself and be subject to errors. Advanced data class features. We can add validation logic with the dunder post init method. For example, here we validate that self.age is a positive integer. And if we try to initialize person with a negative age, it raises a value error. And this is a very fast way to add validation to your Python classes. You can also have a data class inherit another data class, which will extend their functionality. We can use the field method in data classes to customize how fields behave. In this case, we can use the argument init equals to false. This tells Python not to include completed in the init method's parameters. If you have this class with completed and it defaults to false, this still allows you to initialize the task with completed to true. But if you want to enforce that this will always be false, you can use the field init equals to false, and then in the post init, you set the default value of this field. If we run this, it works fine, but if we try to add completed equals to true, we will receive an error because we're injecting one extra argument into the init when we're explicitly not allowing this. Async IO. Async IO is a Python library used for writing asynchronous programs. It helps manage tasks that may involve waiting, such as network requests or file I/O, without blocking the program's execution, making your code more efficient and responsive. Why should you use async IO? Well, you can achieve concurrency without threads or processes, and the library allows you to handle multiple tasks concurrently within a single thread. This is great also for tasks like network communication, database queries, or reading files where waiting is common as you won't block it. It can also improve performance. In IO-bound programs, async IO can be faster and more resource efficient than threading. Some of the key concepts are coroutines. This is a special type of function defined with async def. It represents a task that can be paused and resumed. Here, the await keyword is used to pause a coroutine until the awaited task completes. The async IO event loop runs coroutines and handles scheduling. Think of it as the engine that manages which coroutine runs and when. Here we have two coroutines where one is sleeping for 2 seconds and the other for 1. Async IO.gather schedules both tasks to run together, pausing each one as needed. As you can see, we start both tasks at the same time, but task 2 finishes before because it sleeps for 1 second less. So we finish this task and then we're able to finish task 1. Unlike using time.sleep, which pauses your entire Python program, async IO.sleep allows you to run other tasks during the delay. And async IO.gather is how we run tasks concurrently and return the results as a list. You can use async IO.queue to manage communication between tasks. Here we gather a producer and a consumer, and we inject the queue into both of them. In the producer, after waiting for a while, we put an item into the queue. In the consumer, we can then consume the item that the producer put in the queue. Asynchronous programming has many use cases, such as web scraping, where you're fetching multiple pages concurrently, database queries, so you can execute multiple queries in parallel with an async database driver. Microservices can allow for high-performance web services or APIs, and real-time applications where you can build chat applications, stock tickers, or real-time dashboards. Alright, that's it. 50 advanced Python programming concepts. I hope this will help you in your interviews as they surely have helped me. Like I said before, all code examples are available on the GitHub repo in the description. If you made it this far, please let me know. And if you'd like more rapid-fire programming tips videos like this, leave me a comment. That's it for this one. Thank you so much for watching, and I'll see you later.